Today we're going to be going over the grade 10 physics power focus areas, energy representations 1 and 2. Mainly, I guess, more towards 1, but we'll also definitely touch on 2. And we're going to go through some vocab terms and explanations, and then we'll go through some example problems after that from the diagnostics. All right, vocab terms. So one of the first things you're going to need to know when doing these content are what force is, and we're also you need to know potential and kinetic energy, but that's something you should already have some idea of. So I'll go over that in the next slide as more review and further explanation. So for force is something that influences the motion of an object. It's usually a pushing or pulling motion, like with a wheelbarrow. When you pull it backwards, that's pulling motion. When you push it forward, it's the pushing motion. You are the force that's acting on the wheelbarrow to make it move, right? So the force formula is mass times acceleration. So the work divided by distance, we'll go over. The work is a bit down below, and I'll come back to that and explain why work divided by distance also works. But the force formula is mass times acceleration, because depending on how big the object is and how fast it's going, it's gonna uh, have more force on the object depending on how big. Like, let's say there's a car, right? Let's say it's a very big, right? So it has a lot of mass, and let's say it's going at 70 miles per hour, and then crashes into something. How big the crash is affected by how the force or the mass times acceleration. So if it's going faster, the force is going to be larger, right? And then displacement is the second vocab term. The displacement is the change in position of an object due to force. You can think of it like distance. It depends like where the object is moving from its starting point. Like, let's say your car starts from your house, and you're driving to school. That's the displacement, is like how many miles you drove, right? So for the formula for displacement is velocity, or not, how many miles you covered. So the formula for displacement is velocity times change in time. So the velocity, let's say, would be miles per hour, and change in time would be how long it took for you to drive to the school. So if you're driving at 30 miles per hour on average throughout when you're going from home to school, and then you multiply that by, let's say, 50 minutes it takes you to school, that's the displacement. And velocity, as we mentioned just now, is speed, except it takes the displacement and direction into account. So not just distance. So velocity can be negative, because distance can't be negative, right? Like, if let's say you start in the middle of a road, if you go backwards, you have a negative velocity. If you go forwards, you have a positive velocity. All right, and then we have work, the energy transferred into an object when it's moved by force in the direction of the displacement. All right, and before we go through the last vocab term, work, I just want to mention really quick that when we talk about mass, it's usually going to be in kg on the content assessment. But if not, remember to convert. But that shouldn't be a problem. But I get when you're doing like problems like outside of the content, maybe you're often going to want to convert to kg if it's in a different unit. And then final vocab term on the slide, work. Work is the energy transferred to an object when it's moved by force in the direction of the displacement. And I'll go further in detail what work like is on the next slide when we talk about kinetic and potential energy. So the formula for work is force times displacement. So that's why for force and displacement, I have two formulas, because depending on what information you're given, you're going to want to do different equations to get a certain something. Like, if you're given the value for work and the value for distance, and you're trying to figure out force, you would do work divided by distance. If you're given the value for work and the value for force, and you're trying to find displacement, you would do work divided by force. And then finally, as I just said, if you're given the value for force and displacement, and you're trying to find work, you would do force times displacement to get your work value. All right. So potential energy is the energy stored in an object depending on where it's positioned. More potential energy in the object means more work being able to be done, like on the object, which results in more kinetic energy. So, like, let's say you have a box that's really on a ramp that's really high, and then you The higher it is, the more potential energy it has, because when someone pushes down the ramp, and if it's higher, that means it's going to have more speed, which means it's going to go faster. It's going to have more kinetic energy because you have more potential energy to transfer into work, which will cause more kinetic energy. All right, so I actually had something down wrong on potential energy. So uh, forget forget what you saw, earlier. I just made a cut here. So the formula for potential energy is mgh, or mass times the acceleration due to gravity times the height. So mass, obviously the kg value, the height probably in feet, and then acceleration due to gravity will be something meters over meters per second squared. So m/s and then squared. That's the value you have for acceleration due to gravity. At least based on the diagnostic, there are not many questions where you might need to calculate potential energy. Usually it's kinetic energy, but it's still good to know just in case, and just to better understand kinetic energy as well. So for kinetic energy, that's the energy that object has because of the work done on it. That is possible from the amount of potential energy. So, like I said, more work means that there was more potential energy if more work is being done on an object. So that kinetic energy will cause a change in the velocity of the object, which in turn changes it into kinetic energy. Or sorry, the work done on the object will cause a change in velocity, which in turn changes its kinetic energy. So the approach, just something to remember that'll help you with the content. The work done on an object equals the change in kinetic energy. So the more work done on the object, there'll be an increase in kinetic energy. And the higher it will be. So the formula for kinetic energy is 0.5 times mass, which is the kg value, times velocity squared. So you can just do this as, there's no like order of operations here. You can do it in any order. You can just do 1/2 times mass times the velocity squared. But remember, the velocity squared has to be done first, and after that, you can do it in any order. You can multiply everything in any order. All right. Further explanation. So when potential energy is higher, kinetic energy will be low, and vice versa. That's because kinetic energy is caused by potential energy being released. So when the potential energy is high, let's use the box example, when the box is up on top of the ramp, there's no kinetic energy. The box isn't moving. As the box moves down the ramp, when someone pushes it, the potential energy will get lower and lower, and the kinetic energy will get higher and higher as more velocity is gained. And a quick basic understanding of something before we go any further. The law of conservation of energy is the total energy in an object is not increased or decreased. It's always transformed. So when you see kinetic energy and potential energy get lower or higher, it never just goes somewhere random. It always stays between each other, or also thermal energy, which I will explain later. But like when an object is dropped from a high place, potential energy, as I said, is transformed to kinetic energy. That energy just doesn't like go at nowhere. When the potential energy gets lower, kinetic energy will get higher. As simple as that. So potential energy plus kinetic energy will equal your total energy, at least for most of the problems you'll see on the content assessment. And just some quick vocab, you should know for some more vocab. Joules are the unit of energy used in physics, often used in physics to represent when a force displaces an object or mass. So for work, pretty much, that's joules is the unit of measurement that is gonna be used. And then thermal energy is the energy in an object that is responsible for the object's temperature. It's not relevant to energy representations 1, but it will be to 2, and which I'll explain more on the next slide. And then same with friction. It's not really relevant to the energy representations 1, but it will be to energy representations 2. So friction is a force that makes an object resist motion on a surface. Think like when like sandpaper has a lot of friction, because when you rub it on a surface, you feel like the two surfaces are sliding together, and then it's like resisting the sandpaper. So that's why it feels really rough. All right, so this is for energy representations 2, talking about roller coaster and skate ramp energy. Sorry, give me a sec. All right, So there are three different types of energies involved with the roller coaster problems: kinetic energy, potential energy, and thermal energy. When, let's say, when the roller coaster cart is at the top of the roller coaster ramp, it starts with a certain amount of potential energy. So as we said, the higher the ramp is, the more potential energy it has. When the cart goes down the ramp, the potential energy is transformed to kinetic energy. As it speeds up, more and more potential energy is transferred to kinetic energy as it speeds up and as it goes down further on the ramp, until it's at the bottom, and then it has to go up another ramp. As it goes up another ramp, the kinetic energy is once again transferred into potential energy, and then the cycle repeats and repeats until the roller coaster comes to a full stop. Now the roller coasters also have friction. This is like a real world thing, right? But you won't have to really use that in the content assessment, at least not for roller coaster problems. At least and if you do, what I'm going to explain here is going to apply to roller coasters as well. But you'll at least use it for skate ramp problems, like a guy on a skateboard on sliding up and riding up and down a ramp. So the same concepts of kinetic and potential energy apply to the skate ramp problems as well, as we just explained. And for friction, the larger amount of time the skateboard or roller skates or whatever move, the more friction will develop from the wheels of the skate and the ramp sliding against each other. So it's going to slow down, right? If there's no friction, let's say you had a U-shaped ramp. If there's no friction, the skateboard would go up and down each side without stopping. Because of the friction, it slows down over time and it'll come to a complete stop. And as time goes on, more potential energy and kinetic energy is transferred into thermal energy created by the friction. So total energy still stays the same. It's just the potential and kinetic energy is being transferred into thermal energy. Because think about it like this, and you might ask, why does friction cause an increase in thermal energy? Think about it like this: when you rub your hands together, right? That's sliding two surfaces against each other, and that creates friction. And when you do that, your hands get warmer. That's why people, when they're cold, they rub their hands together. The friction causes warmth, which causes an increase in thermal energy. All right, so I'm going to go over we're going to use this to just, quickly show you a visual example before we do the example problems. Right, okay, so let's start with no friction. Let's say the person starts at the ramp at the top. You see that the potential energy is very high, the total energy is the exact same. As the person goes down the ramp and up and down the ramp, right? As it starts from the top, goes to the bottom, kinetic energy increases. And then as it goes from the bottom to the top, other side of the top, the potential energy increases. And then once it goes back down, kinetic increases, potential goes down. Total stays the same the whole time, right? Thermal energy is none because there's no friction. But let's use friction here, right? The longer the skater is moving, the more the thermal energy increases. The longer it's going, increases more and more. And by the time the skater comes to a complete stop, the thermal energy it won't be only thermal in the total, but there will be nearly the same depending on where the elevation is, right? So if it's like right here, let's say right here, let's say it comes to a full complete stop at the bottom. There's no potential energy because there's nowhere to go down. You're at ground level, so the thermals equal to totals. But if you stop at a higher level, there'll still be some potential energy. And you see the kinetic energy completely drains away. All right. And we're going to go over some example problems for both contents. All right. So number 1 for energy representations 1 and the diagnostic. The image shows a force versus displacement graph. What does the area under the graph line represent? So the x-axis would be displacement, which is 3.5 meters. And then the y-axis would be the force, which is 78 newtons. If you don't remember newtons from previous contents, that's just the unit measurement for force. All right, so the area under the graph. So what do you do to get area? Let's think of this as a square, right? And then what would you do to get area? You multiply the length times width. Here, this side right here is 3.5, right? And this side right here is 78. So length, right? The 78 is the length, let's say, and 3.5 is the width. We can multiply those two together, and then we get a value, some value. When we multiply force times displacement, what do we get? We went over this in the slides, right? We would get work. So the answer here would be work. When you the area under the graph line would be work, because when you multiply these two values, well, whatever they are, you're gonna get the value for the work. All right, I'm just referring to this real quick, and we're gonna do another example problem. We're gonna go number 2. A bicyclist with a mass of 1,000 kilograms, or 100 kilograms, sorry, has 1,250 joules of kinetic energy. What is the velocity of the bicyclist? You know, I'm butchering that, but you get the word, in meters per second. Okay. So, okay, so if you're given we know this is the formula for kinetic energy. So we want to isolate velocity because we're trying to figure out what the velocity is. So what we would do is multiply both sides by 2. That's to cancel out the 1/2 on this side. So then you would get, here, let me pull up a whiteboard real quick so you guys can get a better visual idea of what I am trying to say here. All right, so we're gonna have what, 1/2 mass times velocity squared, ke. Let's say we know ke equals 1250, and we know that the mass is 100 kilograms. So 1/2 times 100 velocity times velocity squared. So what we're gonna do is multiply both sides by 2, so we can cancel out the 1/2 and try to isolate the v. So 1,250 times 2 is equal to 2,500. So now we have 100 times velocity squared. Then we're going to divide by 100 on both sides, right? So we can cancel out the 100. So then we're left with 25 equals velocity squared. And then we know that what squared equals 25? That would be 5, right? So the velocity equals 5. There we go. All right, and I'm going to go to number 9. Because I'm not going to do all of them because some of them are repeats. So you'll know how to do these. So we can just, you'll know how to do these from what I've already went over. And some of them are just basic definitions. All right, so a car with a mass of 1,200 kilograms is moving at 10 meters per second. How much kinetic energy does it have? So this is just plugging in. This is even simpler than the last problem. You're just plugging in 1,200 for the mass, and then 10 for v. So 1/2 times 1,200 is 600. 600 times 10 squared, which is 600 times 100, would be 60,000. So I'll show this right here. Reload, refresh. So 1/2, right, times the mass, which was 1,200, times 100, or sorry, 10 squared, which is the velocity. So that'd be 600 times 100, right? If we could do that. And then that equals 60,000, which we have right here. We're going to go over 2 more problems in this one, and then we're going to do 2 problems in energy representations 2, and we're done for the video. So a car with a mass of 1,200 kilograms is moving at 20 meters per second. If the car doubles its speed, how will the kinetic energy of the car change? You might think all you have to do is, increase by a factor of 2 because it says double. That would be true if there wasn't a squared right here. So what's easiest to do if you don't know any tricks is just to plug everything in, right? So we can do 1/2 times 1,200 kilograms is equal, 1,200 kilograms times 20 squared. So 600 times 400, which would be equal to 24, or sorry, 240,000, right? So we know that, the base value is the kinetic energy is 240,000. If you want to, it's saying double the speed. So that means we're doubling the velocity, right? So that would be 40 squared instead. So we would have, instead of 400, we would have 1600. And 600 times 1600 would be, let's see, let's calculate correct. I'm too lazy to. 960,000. So then we'd have 960,000. So now you could do 960,000 divided by 240,000, or you could just do 96 divided by 24, and that would equal 4. It will increase by a factor of 4. And if you want to know a trick, it's squared, right? And if you're doubling the speed, you just think of it as like the trick. Okay, you know what? Let's say it like this. The trick is, if it was triplet speed, you just do that squared, and then so it'd be by a factor of 9, because we have a squared right here. So since it's double, the factor is 2, but then we have to square it because we have a square in the equation. So the factor would be 4. If it was quadruple the speed, the base value is 4 for the right, but then we would have to square that to get the factor because there's a squared in the equation, and then the factor would be 16. All right, and then we'll go over one more on this. Number 14. A rock falls on a cliff. Based on the information in the graph, how much work is done by gravity? You don't even just ignore the by gravity part. It sounds confusing, but it's just asking how much work has been done. Right? So we already know how to do this. We would just multiply 80 times 11.5, and that would be 920. All right. We're gonna end it off with 2 diagnostics from this one, from Energy Representations 2. Sorry, we don't have more. There's only 3 questions in the diagnostic. So a skateboarder reaches a position on the ramp shown in the image. Which bar graphs her potential and kinetic energy? So you know what, when the skater's at the top, it has to have higher potential energy than kinetic energy. So we can cross out A, and we can cross out D. So we're left with B and C. We know at the top it has the most potential energy. So the potential energy should pretty much equal the total energy. Here, clearly, it's not like that. It's more even. So it would be here. Very little kinetic energy because that's the top. It has the potential to, have a lot of kinetic energy as it goes down, but it doesn't have a lot of it yet. Finally, a 2,500 kilogram roller coaster car is waiting at the top of a 30-meter hill. What are the potential energy and the kinetic energies of the car? All right, so I'm not gonna go through the kinetic energy since we've already done that, right? So many times. So I'm just gonna do potential energy here. So we know potential energy is mass times the acceleration due to gravity times height. In this case, we do not have the acceleration due to gravity. So in that case, don't get too confused. You can just multiply the mass times the height, and that would equal, in this case, that would equal 75,000. So the potential energy is. Wait a second, what? All right, so the final problem, a 25 2,500 kilogram roller coaster car is waiting at the top of a 30-meter ramp or hill. What are the potential energy and the kinetic energy of the car? So here's a trick. You don't have to use any formulas in this problem to figure out the potential or kinetic energy. We can just tell what the answer is based on the position, right? So it's at point one in the image. That's the top of the roller coaster. So that, remember, as we've gone over, that means the potential energy would be at its highest, and the kinetic energy would be zero or close to zero because it hasn't gone down the ramp yet at all. So it still only has a potential to have a lot of kinetic energy. It doesn't have any kinetic energy yet. There's been no work has been done on it yet. So that, I mean, we only see one answer that has kinetic energy of zero. That would be C. And that's it for the content. Thanks for listening. I hope this helped at least somewhat, and this wasn't too confusing or too rambling. And you can always, email the tutoring club for or come to tutoring club sessions at Summit Tahoma if you're a student here. If you need any help further with this or any other contents, or you can or you can contact me, which is Ashwat Avamal.ta at mysummitps.org, AVIMAL, and the tutoring club Gmail is Tahoma Tutoring Club at gmail.com.